go live. This is preparing live stream.
Yeah, what's up with Jeremy though? Has he?
1 second, and it says we are live. We should be live right now. Go live. Oh, yeah, we are live on YouTube, and we're joined with Aiden Schaefer. Say hello. And,
Hello, everybody. Hello, the future.
And Wayne, the infamous Wayne Ojala from Fail Forward Research.
Oh yeah.
Ohala, or you say jaw? I mean, you're of European descent, so it should be something like Ohala.
No, I'm not Spanish. It's actually a Finnish name. So yeah, it's the ja sound.
Oyala.
Oyala. Yeah.
Oyala. Okay.
If you wanna say it that way.
I'm not a Finn. I'm an American.
Well, I'm a Canadian.
You're a North American.
You know.
We're East Coasters over here. We got Tom Butler, of course, the infamous, helping us out at the lab. Wayne Ojala has been running some experiments. Some of them take several hours, 8 to 10 hours. You were saying some of those experiments ran? Yeah,
they're these ones are long-term ones, you know, over a few hours, taking samples and weights, measuring weights, you know, periodically over long periods of time. Yeah.
It's basically just a cup of seawater on top of a magnet, and you're just weighing that over time and controlling for evaporation this time. You're still seeing weight loss, right? Wayne?
Yeah, I'm here. Sorry, I had something.
I was saying that you're controlling for evaporation in the sample. You're still seeing weight loss. Is that correct?
Right. Yeah. Like all the things I suspected so far as being causes. Just a moment. Causes like evaporation or corrosion of the magnets being in contact with the salt water, which does happen. So I thought some of the gases formed from that reaction might explain what I was seeing as far as weight loss. But the experiment that I ran last night and today confirmed that there was or seems to be a decrease of up to, in this particular experiment, 20 milligrams of weight loss in this little glass jar of salt water. So yeah, that's kind of interesting. And I just about finished editing a video on this. I'm going to be uploading it probably tonight or tomorrow. So yeah, that'll be on my channel, Fail Forward Research. Hit the subscribe and notification, and I mean smash that notification bell. You'll probably see it come up pretty soon. And so yeah, Aiden was asking me what I think is going on, and the best way I can kind of theorize is, or explain, is that the magnetic field gradient is polarizing a small portion of electrons or nuclei in the sodium and chlorine ions, and that's creating kind of a shift in the energy density of the vacuum, which could be resulting in a small force. So the whole thing, presumably, I think, might be wanting to move, in this case, upwards or away from the Earth's gravity. Or there's still more work to do to figure out if this is directional or if it's just kind of like, you know, all-encompassing, omnidirectional anti-gravity, or if you get what I'm saying.
there's a couple ways. I'm sorry. I do believe in Bob Lazar, so I'm not sorry because I grew up in Los Alamos during those years that he was working up there. But so warping, like I believe he was telling the truth. So like the Zeta craft, which may be the same, or that the sports model looks exactly the same as whatever Billy Meyer photographed.
Mhm.
They were distorting space-time in front of it, right? And so they had these directed energy systems.
Mhm.
There's another possibility, because like I was explaining earlier, which isn't live, but when I've seen optical cloaking, the shadow of the vehicle spun off. Like I'm trying to do a twisting maneuver with my fingers to the people
Sort
that
of like
watch.
an iris, closes in
Yeah,
on it.
like a camera iris, right? Like imagine if you can a camera iris and you open it like in the opening of James Bond, but
Yep.
that's coming off of a vehicle. The best way I've said it in the past is like you get a spherical object and you throw it and it spins into confetti and disappears. It spins off of the original object.
What do you think is causing that?
And just to recap briefly, the last time I had a real UFO discussion with somebody in the military, he was a sonar operator, a guy watching the funny screen, and he said the vehicles they were able to take measurements, or they could see that the field was spinning slower around the vehicle. It could not fly as fast underwater as they do in the air.
Just 1 second. Wayne, I muted you for a second because there was some background noise. So yeah, that you were saying they change the rotational speed changes as it enters water versus
Different
air.
mediums, including a gravitational field, right? Like if a denser object, I mean, we know this is general relativity, excuse me.
So
But
basically out in the Kuiper belt, it'd be spinning at one speed, close to Jupiter, different speed, in an atmosphere, different speed.
right. Gravity field plus medium. Like if there's like more oxygen, if there's a denser atmosphere, it's going to have to push the atmosphere around, and that's going to be one frequency. And then on like a Fourier series, and then you're going to have on top of the gravitational frequency, the water, the hydrogen, the oxygen, whatever. It's a bell curve. In this case, I bet the control system applies statistics. Like, our atmosphere has an average weight. If you're like over a crowded city like Mexico City, like Beijing, where there's a lot more carbon in it, the density of the atmosphere is going to be a little bit more because of all of the particulates. And then underneath that is going to be the mass concentration, the gravitational field strength, the field polarization strength in that region specifically, right? Like mass cons, like we haven't gone into that, but the Apollo missions, when they're going around the moon, this is NASA lingo, it's a mass concentration. And then they found out that the orbital altitude of the Apollo capsules, the command module, it would be attracted if there were like mountains because the distance was smaller. And then it would also be attracted if there was a heavier concentration of heavier elements. So then go back to that Earth geoid model. When I was studying the frame dragging thing, like the gravitational field of Earth is not uniform, but we're taught in our textbooks it's negative 9.8 meters per second squared. So there's got to be, that field density is a frequency, and somehow pi relativity, let's find the right mathematician on that part. So
There's also a gravity probe B that
That's yes.
found some frame dragging effect as Earth was spinning, that like the gravity wasn't actually pointing directly toward Earth. It was a little bit off.
Right, because the Earth has a mass concentration, which is causing space-time to curve around it, but it's much smaller relative to the sun, which is, it's like 300 plus Earths fill up Jupiter, and 1,000 plus Jupiters fill up the sun. So the
300,000.
overall field density of our solar system is controlled by the sun's mass con, and then we're on 1/r², 2 point whatever, and then we get out to Earth, and then Earth is another mass concentration. So the frame dragging of Earth's mass concentration working against the solar system frame density is what's happening. And then that's what gravity probe B measured, is the drag, the inertial drag of our gravitational field relating against the sun's, I don't have a big enough ball, but the sun's gravitational field.
Yeah, the ball will be about the size of your house.
Uh,
Ball for Earth.
yeah. It's much bigger. Like, I mean, the Earth is like a seed, and the sun would be like the Earth is a tiny seed, and the sun is a basketball.
Right. So getting on to what we're doing tonight, we're working on dynamic nuclear orientation, or via EPR, electron paramagnetic resonance. So when you see here this large electromagnet, which is above me in the picture, there is a waveguide in the center of it, and we're bombarding samples at the Larmor frequency of the valence electron. So that would be about 28.025 gigahertz per Tesla. We're not going to put in 1 Tesla. We're going to be doing less than a Tesla. So it'll come out to around 9.5 gigahertz, which is way up in the X band of microwaves. And we're hoping to see some weight loss in various samples. It does take quite a while to set up an experiment like this. So question is, what sample we should try tonight? We got a box over here full of all different kinds of goodies. We got the densest element on Earth. This is osmium. That's a really cute. These are kind of cool. Slightly bluish metal, extremely dense. That I'm not so sure if this will attract the EPR so well, because it doesn't have that many free electrons. I know we talked about that earlier. Someone suggested, Michael Himes on LinkedIn suggested I try aluminum, but with very thin aluminum. So for that, we've got Mylar thermal blankets, which are basically plastic with a very thin layer of aluminum on them. So if this works, it would be pretty exciting. The problem with this material is that it's extremely lightweight, and we're using a mechanical scale to measure for weight loss. So I'm not so sure if that will be a problem at all in seeing a result. But we could give it a shot. We could cut off a nice large chunk of this and see if there's any weight loss on that. We have various materials, powdered metals and epoxy. We have aluminum, iron, niobium, bismuth, trioxide, vanadium, copper, nickel, zinc, nickel, silver, tin, and magnesium. We've already had some trouble with the magnesium because it tends to light up and just go poof when we put too much power into it. So first question is, which one do we want to try tonight? Phil Cosmos says try the aluminum. I'm watching on the YouTube channel, that is. Aidan, what do you think we should try?
I don't remember. You'd have to show me the sample page again. I was down in like the 23, 24 range.
Oh yeah, let me pull that up. 1 second. Share screen. That would be there. Okay, so what we're looking at right now is all of these samples. This is the actual composition of these little pucks that I have over here. Each one of them is about 1.25 inches in diameter and 1/16 of an inch thick. I don't know if my camera's on right now, but that's roughly what they look like. You said 23, 24?
Yeah. No, I was interested in 23, which is the niobium and bismuth trioxide. Maybe it was more like 26, and then definitely 28. And then I'm going to interject like my last objection is that you're using straight magnesium and it has to be bound with a silicate. So we have to get that magnesium orthosilicate and go through and remake some of these so they don't catch fire.
We could try turning down the RF.
You're gonna no. You're pumping too much energy into it. So there's enough excess energy that the oxygen in the atmosphere surrounding the sample is going to start vibrating with the magnesium, which is where the magic smoke is coming from. Oxygen feeds fire.
Yeah, but we could fill up the chamber with like carbon dioxide or argon gas.
Okay, just please order some of the magnesium orthosilicate powder, and let's make a couple of these with that instead.
Yes, I definitely will. That's on.
Thank you.
That's on order.
Thank you.
Magnesium is not going to do anything. If you're trying to do DNO, it's not going to do anything.
I know, but the magnesium orthosilicate looks like a bar magnet at the molecular level, and then the oxygen, because it's a silicate, it protects the magnesium. So
so the molecule has a magnetic moment.
Yeah, look at it. Look at the structure. I've bitched about this over the last year. Jacques Vallée, as soon as it started with listening to Jacques Vallée on Joe Rogan, and as soon as he said magnesium orthosilicate, like something, the bell went off, and I stopped, and I was like, "What is that word, orthosilicate?" And then I looked it up, and then it reminded me of a chemical joke. I was trying to figure out if you could like baste something in a chemical that would make a turkey magnetic, and so you could stick it on, cook a turkey in a weird fashion. It turns out these orthosilicates, like if they're fluidic, are pretty fucking nasty, like the osmium tetraoxide stuff. But once they're solid state, it's a silicate, and then you can turn it into a ceramic, and you can structure it and get a very interesting disc-shaped shape that's made out of this structure that wants to, I think the structure why the aliens are using it is because it allows the nuclear spin pulses to go through the vehicle, which is what you're seeing as the gravitational field, that Mr. Lazar talked about, that he felt like he was strangely attracted to. It's an external amplification of the strong nuclear force.
How about this, Aiden? We can use the aluminum on the Mylar.
Okay.
And stick a little piece of the osmium in that. Make it look a little ball. So the aluminum would create the dynamic nuclear orientation and transfer that to the osmium, and then we'll see a magnified.
You're not seeing, that's not dense. No, we've got to be trying to affect the osmium, and then that's going to affect the aluminum.
Osmium, I looked at osmium. If you look on the NMR charts, it doesn't have much in the way of nuclear spin, so you're not going to get that.
No, it doesn't. It doesn't. But
so it's got density.
It's got the density. It doesn't have
Yeah.
the need to spin.
So
But
if you
I'll-
put the,
polarization.
if you
Okay.
put the aluminum around it, you know, you get that mass density in the middle, but the aluminum around it might give you the effect of what you're trying to do with the
Exactly, that's
DNP
what
or
I'm talking
DNO,
about.
which might affect, you know, the space around it, and then you might see a shift. If you can get like an asymmetric distribution of this nuclear orientation, so you might kind of like on one side of this little sample, it might affect space or affect the vacuum energy density on one side, so you get a gradient, kind of like what I'm seeing with my experiments. And then it looks like the thing might start moving. So if you can get your little camera in there and look for movement, maybe not so much weight loss, but
Outward.
look for movement, right? Like if
or
there's, like any sort of movement,
outward.
swaying of you know, where this thing just starts vibrating or moving or whatever in the.
Also the string.
It's
Yeah,
gonna
that's
be
kind of what I was thinking about.
this, like I'm pointing, like this looks like I'm pointing up, Wayne, but that's outward, right? This is inward.
Just a second here, I gotta see it.
Oh, okay.
Hold on.
Sorry, the outward,
Okay.
right? Like Z positive, Z negative.
Yeah,
That's outward. This is inward in the gravitational field or gravity field, right? Outward. So if we're starting to affect its gravitational polarization and find equilibrium or pumping energy into it, it should start moving
Something like
outward.
that.
And we're calling it up. Okay.
Yeah, something like that.
No, I'm not. We're parsing, and I agree. I'm
Yeah.
not trying to. It was one of my better. I had a really good afternoon one time at UNM, and I was standing by there's a duck pond in the center of the campus, and if you go into the physics and astronomy department building, there's a thing of Albert Einstein. It's almost life size, so you can be like, try to talk to Albert. But I went out and I stood next to the duck pond, and I think for the first time I could really understand that I was standing on a sphere, and that was outward and this was inward. And most of my life I've been saying that that's up and this is down, because I'm thinking in planar 2D, and that's just part of our education. So yeah, it's thinking in 3D terms. It's simple, but it's not. I mean, it's just something you have to reinforce. And then what really is up, right? Like, is the center of the galaxy up?
I mean, we all know that north is up because that's where most of the people on Earth live.
Yeah, but we're going through a fucking pole flip. So north is now going to be south, and south is now going to be up north.
I don't know about that pole flip thing. Maybe
it started in 1859 with the Carrington event, and look up the South Atlantic anomaly.
Guys, we should. I don't know if you've probably dug into this, but the Bermuda Triangle and what that's all about.
Yeah, there's the Bermuda Triangle and the Dragon Triangle over by Singapore, Philippines. That's the Dragon Triangle and the Bermuda Triangle are where the next pole structure is going to emerge. And then due to the rotational forces, the magnetohydrodynamics of the mantle and the core, the pole structure is going to migrate over 1859 to, it's going to take a couple centuries to migrate from where it's emerging back to the rotational symmetry, because the overall polarization of our solar system is going to force our electromagnetic field to realign with the spin dynamics of the planet, which is still in resonance with the sun because of the the density, the field density that mass concentrations create. And then since the sun is an active nuclear moment, the sun is active. It's an active nuclear moment. Like most matter is inert. It's a non-active nuclear moment. And so when fusion and fission is happening, the moment is active. Blah, that's a new concept to you guys. But anyway, so the planetary magnetohydrodynamics is in resonance with the sun, and the sun is the larger force on space-time. So the electromagnetic force, since it's so weak compared to gravity, will eventually spin.
You mean the other way around? You mean gravity is so weak compared to the electromagnetic force?
Oh, true, but is it though? I mean, it's ephemeral. I mean, mass is mass, and the inertia of the mass is going to keep going. The inertial moment. But yeah, you're right. I did fuck up. Electromagnetism is much stronger, but gravity seems to be, it's the external amplification. Oh, and this is where we're batting up against our current physics. So, but I think it's the density of the planet, its inertial mass is bound to a harmonic within the sun, and the sun is still much larger. It's the dominating moment within our solar system. So its rotation is going to continue and will eventually bring around the new polarization back to the physical spinning of the planet. But my answer is that the Dragon Triangle and the Bermuda Triangle are the emerging field structure.
David Perez has a different explanation for that.
No, he was looking at the warp. He was seeing, but think about it, like if the Bermuda Triangle area is a new pole, it's coming out sideways. Look it up on a map, so you can see that the Bermuda Triangle and the Dragon Triangle are diametrically opposed. And then he was studying cross products within the thunder cells in order to see the vortex tube that was creating the space-time warp. It's you got to look at the planetary field structure. My hypothesis, which my argument is based on, is that the Bermuda Triangle and the Dragon's Triangle are the polarization points of an emerging spinning field. So within that region, like it seems very large since it's on a planet, but in the galactic scale, it's point-like. I mean, that's scalability.
Yeah.
Here we're getting the logarithmic mathematics. What is this? Kapton around aluminum.
Yeah, so it's aluminum around a little chunk of osmium, and there's some kapton holding it all together, hanging on a fishing string. And that's going to be our sample for tonight.
Can we, no. I want it to be fancier. Can we do like, get it inside of a milli disc, osmium inside of bismuth with the two shells, and then try to spin it.
Oh, try to spin it? No. Get out. How about
everything rotates, man. It's my, everything rotates. Everything rotates. We're looking at a brief moment. So you're going to catch a moment. Maybe it goes up and then it's going to fall.
Everything.
We're on a rotating planet around a rotating sphere that's rotating around in a giant barred galaxy that's slightly attracted to Andromeda, that's rotating. They're twisting around each other.
And things rotate in magnetic fields.
Yes, they do.
Things that rotate generate magnetic fields.
And yes, a moving electric current generated, or a moving electric field generates a magnetic field.
Even a rotating superconductor makes a magnetic field. You know, and rotating piece of iron will make a magnetic field.
Okay. Yes. Yep.
So yeah, you are true. You are right.
Thank you.
I concur. So speaking of all these rotational wonders, I've been pondering this. Why do all of the planets revolve around the sun on the same plane? And why does the ring of Saturn, why is it go around the equator of Saturn?
Well, I mean, that's relativity. I don't know if I'm using, it's 1 over r squared, the inverse squared law. Saturn is a larger mass concentration. The rings of Saturn are special. Like it's not a bunch of concentric rings.
We got a problem.
If you, I see that. There was a really interesting paper I read while I was at UNM. So 2013, 12, 13. But if you look at the ring structure, basically what you're seeing are 2 long lines that have been wrapped around. You know, there apparently is like one continuous ridge that you could hypothetically walk along. And I don't know if that's pure mathematics or if that's, you know, because what all of the astronomers, they're all trying to figure out, they're taking these pictures and taking measurements. But also Venus counter rotates, and then you get far enough out, and Uranus is actually like one of the poles is facing in towards Earth, right? So it's rotating, but it's rotating along the direction that the sun's dominance on the planetary system exerts. But Venus, Stan Deo says that in his group, his research group down in Australia working on flying saucers, they said that they hypothesized that Venus was caught. It's an extrasolar system. It moved through the solar system, which is why it's spinning backwards, or maybe it's spinning upside down compared to our polarization. Spin is polarization, and then chirality, right? We're mostly right-handed polarization, and then we're looking for left-handed polarization for exotic effects or something.
Yeah, I've heard that before.
I found the element antimonide something, indium antimonide. During the Unlab week-long presentation at the beginning of January, Charles Chase, they mentioned that indium antimonide, when it's excited, the electric field spins around it, and it has a greater electron velocity than carbon fiber or carbon nanotubes. And I guess it's that electron drift velocity that we're trying to figure out.
Yeah. Yeah, that's known to have something to do with, well, propulsion and creating forces when you accelerate electrons.
Okay, guys, so we're just about ready. Over here on the left, top left, you have the spy camera, which is a fiberscope, which is why the image looks so shitty.
That's a bunch of fiber optic cables.
Yeah, we're looking through a whole bunch of fiber optic cables inside the waveguide. Bottom left, we have the analog scale. Top right, we have an overview of the experiment. Here, I'll just move my camera now. You can see everything there. That's that second overview view. Also, this view has a couple more. You can see some other stuff on the side, but really, this is all that we're really interested in. Is that information right over there on the side. And then on the bottom, you have yours truly. And we should be ready to run this experiment just about now. We got osmium. Osmium pellet weighs about 31 grams, 1 ounce, surrounded by very thin aluminum foil on top of Mylar, which is those thermal blankets. Thanks to Michael Hines for the suggestion to try that out. Or surrounding the osmium, because it's a very dense metal. Here's another sample of osmium right here. This is the densest metal or the densest material known to man, and it is a great way to measure for any dynamic nuclear orientation that would be happening in the aluminum, and the osmium will then be affected by it. So hopefully we'll see some change on this scale over here to the left as we power the experiment on. It's going to take a couple minutes, so here we go. We're going to power on the magnetic field, starting up the RF. RF will take some time to warm up. You'll know that it's ready when the standby light turns on. We also have a temperature probe over here. It's going to tell us what the temperature of the sample is. So it's right now around room temperature at 20 degrees centigrade. Tom will be keeping track of that as we run through the experiment to see, you know, in case we're getting so hot that we're going to start damaging the equipment or having things burst into flames, which is undesirable and has happened before. Okay. Aiden, you want to entertain the people in the meantime? I'm going to move this spotlight.
Sorry, one more time.
You want to entertain everyone for the next couple minutes because we got probably about 5 minutes or 3 minutes or something like that until this.
What the hell? No, I'm not a pretty young woman.
And, you know, it's time for anti-gravity.
Start doing kung fu.
Do some kung fu.
Tai Chi. Yeah, I'm getting older, so I've passed
you gotta keep these people entertained because they have short attention spans, right?
Well, the fuck if
Maybe they could play some Minecraft while they're waiting.
Oh my god, the millennials.
Just talk in a really fast voice. Like
No.
Hey guys,
Danny here.
We're gonna do another round of
Wayne, guess who's on the chat? Join the technicians is here.
On what chat?
On the YouTube chat. Jeremiah's showed up.
Join the technicians. Oh, I like that guy.
Miss him. Need
like
to
that
hang
guy.
out and make some circuits with that dude.
Yeah, Jeremiah, you want to pop on to the chat? We're running alzapon experiments. I will PM you the link. Right. The invitation link.
Do. In other news, we're about to go into martial law.
Oh yeah, in Ukraine. This afternoon, a couple here on the western. Anyway, Ukraine's on fire again, so we'll probably wake up to World War III.
Yeah.
But some fuckers blew up a pipeline in far eastern Ukraine this afternoon in the Western Hemisphere time. So middle of the night there. Doesn't look too bad, but
we're ready. Guys, check this out. We are ready.
Good, because we're about to go down that slippery slope of political conversations.
Keep the mask on.
Yeah, limited nuclear exchange. They want some assholes, some alpha males on the planet want to see limited nuclear exchange.
Why not, eh? When you put all that money into nukes and it's good for a test drive.
I mean, I know, and it hasn't been disclosed, but there's got to be a base on the moon. And from talking with aerospace mentors that helped build up APEC over the last year, there's a couple underwater bases. So if the nukes fly, the aliens have like 30 minutes to interact with them, and they're probably watching and can do it within 5-10 minutes.
That's a tall theory.
No, it's not a tall theory, man. It's like I worked with Hastings on the UFO versus nukes documentary. And it they fuck with nuclear warfare. So, and then some of us stupid. It's the human monkey, the monkey mind, the body, the flesh bag has got to go through the paces. And over the years, I'm like, why? You know, it's the law of karma.
Hey guys,
why?
we're ready to start running it. Yep, get that gauge going.
All right.
Okay, we're powering on the RF in 3, 2, 1. RF is pumped into the chamber right now. What's our temperature? Oh, it's right.
I don't know if this is just me, but I can't expand the Mark's camera there. Is that just me?
I see it fully, but I'm at home on a desktop. He's got a complex picture.
Yeah, but usually I can expand the window. I didn't know if that was just me or.
For the record, I'm just changing the Gauss on the electromagnet. So we're at 9.25 gigahertz and 3271 Gauss. 71.8 actually.
Yeah.
And dropping. And we'll take it down to 3200 and we'll take it up to I think it's 3,400.
In and out, busy. I'm doing experiment build.
What's your temperature at?
41 degrees Celsius.
Okay.
That's hot.
Well, it's not as hot as the catch fire temperature.
100 degrees plus 100 degrees Fahrenheit. Like 42 to 44 is somewhere right around 100 and
Those numbers
ugly.
aren't that accurate. With the RF off, it goes a little higher. What was it reading now?
30.
33? Okay. RF on.
So ohmic heating. So we're doing work against our rotational field or gravitational field. Whenever there's ohmic heating, that's because the electric field is not structured. The molecular structure is not structured enough. Orthosilicates. We got to get up into the higher ceramics. They're like the metallic ceramics, this transparent aluminum.
Hey, can you send me a link to that powder, the orthosilicate powder?
Well, yeah, the CAS number.
A link to like purchase it.
Yeah.
Okay, so a positive result in this test, just to clarify, would be if the black arm of the analog scale were to rise. Actually, no, were to drop. If it drops down, that would be a decrease in weight. If it were to go up, it would be an increase in weight. I guess either or, any change in weight would be proof something happened.
Yeah, that would indicate a change in the inertial field around the little ball of osmium, I think. Unless there's a more mundane explanation for it. Do you think your sample is like in the dead center of your magnetic field?
I'm pretty sure it's not like exactly dead center, but we can see in the spy cam that there's not much movement on it right now.
Yeah, from what I've seen, it was like an orthogonal force or something that appears when you hit resonance. It's like orthogonal to the magnetic, or orthogonal to the magnetic flux. Your B field vector.
We should just start making more complex. Make these more complex and somehow, I don't know. It's not, we're shooting it from the outside with RF energy, right? Our RF energy is, what is it representing, right? Like, so tonight I've been arguing.
An oscillating magnetic field.
Right, but So let's go back to nature. Let's talk about the pole flip. Let's talk about that field structure. Like, you know, the sun is the dominant electromagnetic force in a planetary system, a star. And then you get these objects that form around it in these resonances. You know, if you look at our solar system, it's not quite, but it's almost a doubling. Like where the planets form in their orbits it's almost double. So it's the one over the inverse square laws is too precise. It's when I was getting into it deeply at UNM, it's like inverse square, like 1 over 2 point something something something, 1 point something something. Right? That's the inverse square modified by natural logarithm modified by random chance and mass concentrations. But it's these rotational fields spinning off of each other, you know, and so the saucer shape is spinning the propulsion field, and it's spinning.
There's movement in the sample.
Where? God.
I was thinking movement in the sample, but shifting left and right. There you go.
Well, let's watch out for heat. It's not structured enough.
Temperature isn't really moving.
Well,
Temperature is what?
30.
What's the temperature?
It's been studied at 33,
Sorry.
34 degrees Celsius.
34 Celsius. So there's going to be a little bit of air convection, tiny bit.
Again, the sample is that black block on the left,
But-
top left.
But you guys were, the other night, you were heating up. I mean, with the aluminum sample, it was getting hot, but you weren't seeing it move.
That was
So that-
different aluminum. That was powdered aluminum and epoxy.
Okay. My point is, though, if it's heating up then, but you were not seeing movement, that rules out the idea of convection currents due to heating
Yeah,
causing
that
the
was
movement.
getting really hot. Yeah.
So in this case here, if you're seeing movement and you're getting about the same temperature, I think you can roughly say that it's not due to convective air currents.
It happened right around 3173 Cal. Let me bring it back down there.
So are you seeing movement vertically, or are you seeing any horizontal movement?
Horizontal movement.
Horizontal, like swinging.
EMF. That would be just back flux or EMF, right? Secondary
No.
waves.
Because it didn't happen the other night with the other sample, like with Did you do any solid metal, like solid aluminum, or is it just powdered and
Powdered
stuff?
aluminum. This is a very thin layer. Before we did powder, powder heated up a lot.
Okay, because I don't see there being like convection currents in powdered aluminum. If the sample is like solid surface aluminum, there might be some convection currents in that. How are you measuring the temperature of it again?
We're using a thermal probe that's
Thermal probe.
spectrum.
Is it based on infrared?
Yeah.
Okay, because the emissivity of aluminum is very, very, very low. So if you're only seeing, what that means is the surface could actually be a lot hotter, but it's just not radiating much infrared. So you could be getting false readings on your temperature gauge. You know what I'm saying?
Yeah.
Is it pretty easy to just, can you handle the sample and just see, like, touch it and see if it's hot?
I'll have to shut everything down for that. I want to go through the entire range of
Okay.
what makes sense to go through here.
So what are we doing? Have you done any sort of like Faraday shielding on the bottom of the? You're just trying to shield away from the plant, from our electric grid. So we built a box around it. Like the roof is shielded. We've got the metal. We don't have a double layer on the floor.
It's in a copper box.
Oh, I
Aiden,
cut.
so
It's
it shouldn't.
aluminum. It's aluminum with
Oh, yeah.
resistors between the two plates of aluminum. And then the copper, there are points where there's copper, it's grounded into earth. So it's at earth grounding frequency, which is responsive to geomagnetic storms. I agree with you, Wayne. I'm just trying to see the bigger, more complex picture.
Well, I haven't physically been there to see exactly his thing. You have, so I can't really. Just from what I've seen, it looks like there's a copper box between the poles of the electromagnet.
Mm-hmm. Oh, that. Yeah. Yes.
Yeah, so that would function. That would function as a Faraday box.
Okay.
You know, to a large degree, that would
You're right.
absorb or reflect away a lot of, external radiation. Anyways, depending on how thick it is.
We're still tied into the planetary inertial field, planetary gravitational field. So I don't know. Earlier, a couple months ago, I was saying, we're trying to figure out inertial mass cancellation or inertial mass shielding. So like we should be somehow zinging the object and then, putting it on a rail or maybe a spring system. So we can see like when it's energized, we're getting, time.
But its frequency increase or decrease or.
Okay.
Yeah. So.
Yeah, that frequency increase starts getting you into a higher dimension or three-dimensional mathematics. But yeah.
Yeah, the way I think of it is it's well, when you think of inertia and gravity, it's sort of this blob or sphere of an equal distribution of some kind of warping of space or what have you around the object. Mm-hmm. But if there's a way to compress it, or like to compress it, say along one axis or on one plane, then the thing might appear to be more massive along that axis or plane than on the other one.
Mm-hmm. Well,
so that's kind of how I see what I'm observing. That's kind of how I see it. I could be totally wrong, but it just makes sense to me.
Well, yeah. In general, the flying saucer videos that I've seen, based on it, filtered through my experiences in real life, the vehicles are symmetrical. Mm-hmm. So that symmetry, we haven't gotten there yet. Like the Millie saucer is the first. The Millie saucer is the first attempt at like a symmetrical research article. But I know, Wayne, I've seen your videos and you're getting into the frequency pumping and overcoming our, the field effect, the planetary field effect, or the galactic solar system field effect. Mm. But you're not at like Hutchison where he's truly overcome the planetary field effect and seeing fluid being flung Well, what is that? All right, it's not up. Remember, it's outwards. All right, so when you're looking at the Hutchinson videos and you see the fluid going, quote, up, it's going outwards. So it's been, I mean, has it been actually like caught in a moment, an outward expanding moment, or is it being, has he figured out in those samples, he's negated the planetary gravitational moment, the planetary field compression, negated that in that small area, and then that object is starting to feel the sun's planetary field, or the sun's gravitational field. So then it's going outward from the planet and towards the sun.
I don't know. I don't know about that, but I can kind of see what you're saying about moving away from the Earth, moving outward. You know, gravity has got to be some kind of converging energy density or something like that. So moving outward from the Earth is moving through some kind of, differential of vacuum energy gradient, something like that.
Right. Well,
kind of the way I see it.
What was it? I guess I'm salted. I'm biased by reading the Robert Jordan and the Illuminati trilogy, and there was like a really bad saying in Germany, and it's like, today the world, tomorrow the solar system. And then hot on the heels of that is like relativity, right? Like if we go back to Newton, and I'll come back to relativity, but Newton was looking for, in his mathematics, he was looking for the prime mover. Like what is that absolute point, that absolute frame of reference that allows you to see all of space-time, because he was looking for God. He was very devout, very, very driven by God. But so that, like, when early on in my studies of relativity, like, you're trying to figure out your frame of reference, and soon you understand that you're on a rotating planet that's rotating around a sun, a star, which is rotating around a galactic center. So there's rotation upon rotation upon rotation, and then you get into complex wave mechanics. So we're trying to figure out how to counteract a couple of those rotations in order to get a buoyancy. We'll mull it over. I mean, that's just where I'm.
That kind of makes sense. I think the secret sauce is related to rotation and frequency and resonance. It's like it's in everything. Every natural system works on resonance. Everything has a resonance, and everything has rotation at the fundamental particle level. So we tap into those fundamental resonances, we can see interesting stuff happen.
Well, so maybe it's in our quantum mechanics, like the electron shell deformation. Here I'm referencing a lecture from Cosmiac, and when we had one of the guys working on GPS. So they're in the atomic clocks are using rubidium and cesium, and they have figured out the electron shell deformation caused by, if you measure that atomic frequency on the planetary surface, it's a certain frequency, and then when they put the clocks up on orbit, they noticed that it was less, right? Time moves slower the closer you get into a gravitational moment. The denser, I hope I'm not fucking that up, but there's a time gradient.
I think you're right. Yeah. I think you're right.
That time gradient that we're using in our clocks is like I'm raising my hands, but that's a delta, a distance, and
Yeah.
change in distance. And so when they're up in orbit, the electron, the vibration, the wavelength that they're measuring is up here. But when they're building it down on the planetary surface, it's mildly less. And then
A little
they have,
lower.
yeah. So that outer electron shell deformation, that I think if you can measure that between samples or something, that might give you that precise gravitational frequency of the of the field where you're at.
Mm.
You know, 'cause we're frequency hunting with the gravity flyer, and that's what Alexei has said, right? He's like,
Yeah.
Everybody's, we're trying to find the fucking right frequency to get the thing to
Yeah.
start going, oh, it's going outwards now instead of
Yeah.
being pushed down.
Hmm.
Yeah.
So at these resonances, when you hit these resonances, I think it's like when you get atoms and subatomic particles processing at, you know, resonant frequencies, and you get synchronization. You know, the system of all of these particles put together tends to eject excess energy in the form of, you know, random vibrations, and the randomness becomes more organized, and there's less entropy, and there's more order. So when you have a more ordered system, it can't absorb or contain all of the extra, you know, fluctuations and random chaotic motions that, you know, exist in a system that's left to itself. So if I'm making any sense, coming from a kind of a mechanical engineering background, you know, I think of it like, so materials have a heat capacity, right? Like a piece of iron has certain heat capacity. That means like how much energy can it store before it raises like 1 degree Celsius of temperature, you know, and there's like the heat capacity determines how many joules you can put into it, or it can contain at a certain temperature. And so with matter, I think, you know, when it's constrained in a strong electromagnetic field, it loses its gravitational capacity, and it looks like it gets lighter, or it gets, you know, it can't couple as much with other masses. You know, that's kind of where I'm coming from. That makes sense.
Okay. So I was multitasking for a moment.
Oh, okay. I'm just thinking. I'm thinking out loud here, right? So, yeah, I don't know. Did you catch what I was saying about heat capacity?
Heat capacity is molecular movement.
Yeah.
And that's, you know, that's, you know, in our world system, the largest supplier of heat is the sun.
Yeah. So I was just saying materials have a heat capacity, like for
right.
for
I'm familiar.
1 liter of water, it takes about just over 4 kilojoules of energy to raise it 1 degree Celsius. So that's the heat capacity of water. And if you apply that concept to mass, you know, and every mass has its own gravity field. So, and that gravity field is, that mass is kind of like, what is the gravitational capacity of that material? You know how
And
much?
that's the spin structure.
Yeah, that's related to all the spins of all the particles inside of it, I think.
Right. So aluminum, magnesium, copper, the elements that we register or that we recognize as highly metallic are the ones that have the best spin characteristics. But yeah, not Cranston. Who's the guy that wrote that they all told the truth? He was up in
Richard Crandall.
Crandall,
Richard Crandall.
yeah. Yeah, he went through, that book is really useful. There's about 50 useful pages in it, and then there's like 250 pages of nonsense. But the 50 useful pages of it, I did find them on Facebook, and it's like the metals, right? We know magnesium, we know aluminum. You know, I think we should continue to work with aluminum
I had a call come in there.
but it's the spin structures. It was like magnesium, aluminum, nickel, copper. Unfortunately, like something like sodium. One or two of those light metals way over on the left-hand side were useful in this stuff, but I don't know.
Yeah, he believed aluminum. There was a few materials that would be, you know, anti-gravity materials like copper, aluminum, bismuth, and of course element 115. And yeah, I studied I actually have his book. I studied it. I was in personal contact with him quite a bit, but he's no longer doing anything related to anti-gravity. He's had a lot of personal struggles and things. So
yeah, I think he got a miracle
he had a
job.
very interesting theory, which it influenced a lot of where I'm coming from, you know, with the nuclear spin stuff and where, and then when I was reading Alzafon's theory and putting things together, you know, it's like, yeah, there's got to be something connected to quantum nuclear spin and gravitomagnetism and all that stuff, right? How it kind of,
Right.
how they can relate. And I could explain that theory. It's pretty intricate. He ties a lot of concepts together. So basically, you know where Robert Forward was. He was an older pioneer in gravitational research and stuff.
Yeah, Bob Forward Sr.
Yeah, he proposed that if you had a negative mass and a positive mass close together, that they would chase each other indefinitely and self-accelerate, and without violating conservation of momentum. So that you know what I'm talking about. And
yeah,
so
yeah.
That idea, you know, applied to fundamental particles, where you have, according to Richard, he had a whole theory about, you know, like where you had like within every, like an electron and a proton and a nucleus, you had counter rotating rings of these particles. And the counter rotation, one would be like positive mass, one would be negative mass. And normally they cancel each other out. But in a converging, you have a converging gravitomagnetic field, like in a, say, like cone shape, then that would cause the two rings to separate. And when you separate the positive and negative mass rings, you get this self-accelerating effect, you know, and supposedly due to the converging of these field lines and the separation of positive negative mass, you get this system will want to self-accelerate. You get something like a warp drive. That's kind of it in a nutshell. And he proposed that you could do this with a magnetic field that would polarize the nuclei, or you could do it in like a T.T. Brown type conical capacitor. You know, so the field lines go through the material, stretch the orbital electrons, so you get a little magnetic field, like the orbital magnetic field of the electrons spinning around. If you can utilize those to polarize nuclei, the magnetic moments of the nuclei, and polarize them in a converging sense, then you get the polarization of the gravitomagnetic field, separation of the mass rings, and you get a self-accelerating warp drive. You get a self-accelerating system.
Maybe. I mean, it's in rotational, but
it's a great idea. It's kind of complicated to
a
lot of concepts to put
Can you
together.
go to the live chat and see if there's anything interesting there?
Yeah, earlier it was like Alien Girl. Oh, Harold Tavares. Harold is on there from APAC.
Hey, Harold.
What are the expected results from this experiment? Is
Stuff
the weight
will move. Stuff will
Is the-
move. That's the expected result.
is the weight scale sensitive enough to measure any change in weight? What you are doing is exciting. I hope you could get good results. We have some private guy. What is the experiment today? That's the Alzaphon experiment. And then, yeah, so not much. We have some private guys saying we need more sensors, and then Harold and some Curtis Horn. Oh, does not sound plausible. What's the experiment today? Again, Curtis, we're working on the Alzaphon experiment. Working on dynamic nuclear orientation and electron paramagnetic resonance in order to work on inertial mass cancellation, which, if happens, should allow the weight, the sample, to move outwards in our gravitational field, away from the planet, outwards. I hope that got out there. So we have 13 people watching.
And also according to Alzaphon's theory, he viewed anti-gravity and inertial reduction as being the same thing. So inertial mass and gravitational mass would, because it's one and the same thing, you'd see, like, if you could do this in a vehicle, the vehicle would be able to
No, they're
accelerate.
not. You have inertial mass and gravitational.
I'm just, from what I read in the
Okay.
book, I'm just saying this was his viewpoint, that you could, like, if you had a vehicle that ran on this thing, it would be able to accelerate and stop on a dime, as well as not be subject to the pull of the Earth's gravitational field.
Mhm.
And the occupants within such a vehicle would not experience any G forces
Mhm.
during acceleration. So
Well,
that's what I read from the
okay.
book. Whether or not that's how reality is, I don't know.
Well,
But
a thought experiment, here, that came to me while I was at UNM. Again, like during these years were really nice because I could go and have good thoughts about Einstein. But so let's take the thought experiment. Actually, the seed of it is from a display up at Los Alamos at the Nuclear History Museum. And then they have these little cubes with a handle, and they're like, the first one is like, this is the density of water, and you're like, boom, 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 you can just lift it up. And then they go, here's lead, and then you're like, oh wow. And then they go, here's something that is as dense as uranium, and you're like, oh, you pull it up, right? It's like there's a physical difference between lead and uranium. You think lead's heavy, but wait if you ever get to hold uranium. And I don't know how the fuck they're doing that, because you can't have uranium in a public display. So maybe it's tungsten. But okay, so let's say you take a 1 kilogram mass of gold, a 1 kilogram mass of water, a 1 kilogram mass of lead or uranium. No, lead. You have something that's non-radioactive. And and then you
Yep.
have a 1 kilogram mass of something that's radioactive, that's moving.
Yeah.
And then you have to run the thought experiment, and you look at it like 1,000 years later, right? And you know that your object that's radioactive is going to weigh less. Let's say has some sort of radioactivity that's like its half-life is around 500 years. So you come back 1,000 years or 2 half-lives, and it's half or a quarter as radioactive as when you started it, but its gravitational mass will be less because it's emitted energy.
Mhm.
So there is a definite difference between gravitational mass and inertial mass, and you have to get into nuclear physics in order to start it. And that thought experiment, like I thought about it several times with basic, the basic knowledge that I gained from living in Los Alamos during elementary school years or primary school years. So that's when I say like stuff that's radioactive is in movement, or an active nuclear moment, like in a sun or a star. So there's that, we got to start looking at, I don't know. I hope the skeleton of the thought experiment got there, but think about radioactivity as movement against space-time, against the vacuum. And then through that lens, try to understand the difference between inertial mass and gravitational mass. Because those objects, like the water, the gold, the lead, over the 1,000 years, 10,000 years, 100,000 years, they'll still have the same same inertial mass and gravitational mass, but the radioactive element will have less gravitational mass. And then there's got to be the daughter isotopes. That's where we start getting into conservation. Because as it's radioactive, it breaks down and emits stuff. And then you have the mother element and daughter elements. So you add the mass of the daughter elements to the mother element. And then you have to somehow capture all the neutrinos, because there'll be like neutrons and protons floating around, or things that are radioactive, off gas, hydrogen. They make hydrogen, which is why in 2014, or the Waste Isolation Project plant, the WIP site in New Mexico, caught fire because the low-level radioactive junk that they were storing there kept outgassing hydrogen, and then that caused a chemical reaction and set the whole place on fire underground.
Wow.
Yeah, this is on Valentine's Day in 2014, if you care to look. And that brought down 10 flying saucers, which is one of my largest flaps that I've ever seen.
Brought down 10 flying saucers.
It was within a month, and a major group of flying saucers flew over Albuquerque, and then they were taking measurements or some such stuff, and then went over. Are non-radioactive isotopes.
Do you think,
yes, there are.
Are you saying that the radioactive or the radiation disrupted their flight?
We call
Did it disrupt their flight?
What I'm saying is that the Waste Isolation Project plant in February 2014 caught fire due to radioactivity, and then it spewed out mildly hot gas or fumes from its venting system. That does not prove the death, because the particles have. I know, but you got to think about it, Curtis. Sorry, multitasking on YouTube. But I might be wrong. Anyway, trying to be polite. But the Waste Isolation Project plant caught fire because of the low-level radioactive stuff, and it was interacting with clay, and the fire, the fumes that were coming out was hot. It had extra protons, and I think they look for the fast-moving neutrons off of refined matter. There are fast and slow-moving neutrons, as well as fast and slow-moving neutrinos. And as a neutrino, circles around a star, it does work in that planetary solar system against the rotation of the field, and eventually just kind of slows down and becomes a cold neutrino. That's what Bob Grenier was talking about in his ion eaters.
Yeah, I don't have any comment on that. I haven't studied neutrinos that much. So,
well, we gotta get down to the strong force, I believe.
I mean, I read a lot of stuff about nuclear physics and nuclear particles.
Jedi to learn the Force.
What?
No, force is just mass times acceleration. There are no Jedi. Only in George Lucas's mind and Disney. Oh,
You mean the Schwartz?
the Schwartz.
The Schwartz.
Ja, das ist gut. Schwarzwald, ja. Wo
I
ist
watched
mein
Spaceballs
Schwarz?
last night, so I know what the Schwartz is.
That's
It's a good movie, yeah. Yeah, for 1987, that was a good movie.
No, Mel Brooks is a
I think
comedic
all Darth
genius.
Vader there again.
There's this was it Batman versus Darth Vader on YouTube? It's made by like some little fan short film. I think that's pretty sick. I recommend it.
What about Chad Vader, the bodega manager?
I don't know.
That was
I don't know. I haven't seen that one.
Oh, maybe it's just a hidden YouTube gem or something, but Chad Vader. Let me see if I can find it.
Well, Dr. Elzafan, you got any updates there?
I'm slowly creeping up to the right magnetic field strength. The thing is, the Gauss meter is flat up against the edge of the electromagnet, not where the sample is. So I'm giving it like plus or minus a bit of strength in order to call this test positive or negative. I have seen a little jump at 3273 Gauss, which would make sense because if the probe is at a slight angle,
Yeah.
it would be reading just like 98% of it, depending on the angle, up to 0% of it.
Yeah. Yeah,
So,
there's gonna be a little error margins in there for sure, and that's where it takes patience to really fine tune things and keep a sharp eye on what's happening. I found with my little experiment, it was like, fortunately with my function generator, my signal generator, I could dial into the fractions of a hertz. And so that was really helpful in finding, cause and effect. But it still takes a lot of patience and, staring at something until your eyes bleed. At least at the, at least for us, amateurs, I'm sure there's more sophisticated ways of doing this and but I don't know.
Getting close to that sweet spot again. We're at 3269 right now. 3269.1. 2. We're running up like by 1/10 of the Gauss at a time.
Are you pulsing? Are you doing like
No.
Yeah,
you're pulsing it with
hertz.
you're pulsing it? Are you pulsing it with RF?
Yeah, 83 hertz.
83 hertz. Okay. Oh yeah, because you got the aluminum around it, right? Okay. Yeah, 83 hertz. We did the arithmetic, and that is equivalent to 6 milliseconds duty cycle, which is what is supposedly the magic on and off timing of this. That's in the book too. Anti-gravity with present technology by David Alzafon.
Oh, man. Well, we got to think about this more. Like, so what are we're injecting RF energy into this device, and we have the electric field coming down, or no, our gravitational field coming down. So I guess we get some sort of orthogonal movement.
Yeah, like if he's seeing the balance arm move up,
polarization, right? I mean,
that suggests that there's an orthogonal force. So the thing is wanting to be ejected from the magnetic field at the resonant frequencies. When you hit the Larmor frequency of the electrons, or the unpaired electrons in the aluminum, and you excite their precession, you get like, I think there'd be some sort of a repulsion effect. So,
well, I always say a buoyancy. I mean, but repulsion, outward.
So if you look at the vector, if you think about the vector of the magnetic fields, and I mean,
right, that's the large electromagnets are creating a field, right? So we're trying to, yeah, we should be, yeah, we're still frequency hunting. There should, man. Okay. Keep going, Wayne. I mean, you're helping me to visualize it better.
Yeah, if you can think about the direction of the magnetic fields of the microwaves coupled with the direction of the static field, the combination of the two there, we know excites the precession of the electrons.
Okay. Do we, I mean, not to be a bitch, but like the field polarization in the electromagnet, I know Mark created the focusing objects to get that spinning, or it's focused. It's a laminar between the two.
Yeah.
But do we need to like rotate that entire thing correctly? Like, oh, I mean, I'm just because I'm starting to look at we've got the planetary field coming down.
Well,
The
planetary field, I don't know. I don't think about that. Because
it affects everything.
We still don't really understand the nature of that, I think,
It's keeping all of the shit on the floor. So, excuse me, all of the equipment on the floor. So, I mean, So it's there. We're aware of it, but I'm trying to say, like, do we, like, somehow should that electromagnetic system be put on like a 5-axis mill so we can, including the whole RF thing?
Yeah, if easier said than done.
I know.
But if you could do that, that would be awesome, because then you could see the,
Where'd you go, Wayne? Can you, Wayne is, Mark, can you hear me, or?
Yeah, I can hear you.
Okay, Wayne.
Listening in. Gotta pay attention to the experiment.
I mean, I guess I am trying to make work, but we're field polarization is what my mind is ruminating, turning it
I think-
over.
I think you're having trouble understanding why it would lose weight or what
Okay.
the theory is. Is that right?
No, maybe. I'm not, I haven't, it's what I understand is from reading through the book a couple times back in July, or the specific sectors, and then APEC and talking with Mark and Jeremiah.
Yep.
And I get, we're trying to, with the pulsing, you're trying to orient the nuclear magnetic moment, and then it snaps back and then affects the outer valence of the electrons. And then for that moment when the outer valence are spinning around in the correct direction or correct orientation, the theory is that the weight, it's an organization of the electric field around the nuclear moment.
Well, so what? Okay, so again, coming from mechanical engineering backdrop here, and also Fred Elzafon was also an expert in thermal physics, so he understood thermodynamic processes, related to heat pumps and refrigerators, and the magnetocaloric effect, where you've got you've got, if you take a certain material like the gadolinium, you put it in a magnetic field.
Magnetic cooling.
Yeah.
I've heard of
So
that.
he uses that as an analogy to explain what's happening gravitationally. So you pump heat out of the gadolinium by cycling this magnetic field, put the magnetic field on, it'll heat up because now the magnetic field is causing this entropy to decrease, meaning the particles are aligning with the magnetic field, so it's being constrained, the motion is being constrained, therefore it's going to want to dump its internal energy, and you see that in heat. You see that as a temperature increase. And so when you get a temperature increase, then you can remove heat energy into a heat sink, and then you relax the magnetic field, and then what you'd see is a drop in temperature on the gadolinium.
Yep.
It'll start to get colder, and now it's going to absorb heat from the surroundings. So what you have in concept is you have something like a heat pump, and heat pumps that we use all the time in refrigerators works on gas refrigerants that are compressed. They liquefy, and as they liquefy, they dump their heat.
Carnot cycle, I believe. But
yeah. So it's a thermodynamic cycle, and then when it evaporates on the other side, it cools, and then it absorbs heat from the inside of the box or whatever.
So what happens if we try to create a spherical refrigerator? Right.
So what I'm getting at with all this, and what Fred Elzafon, what he's was trying to explain in his theory, was with this process of pulse dynamic nuclear orientation, what's happening is something like a heat pump. You have a compression and then a relaxation and a compression, but it's not a compression. It's like you're squeezing the degrees of freedom of the nuclei, and then you're relaxing them so they can then, so they squeeze, when they're squeezed, they dump quantum vacuum energy or what have you, whatever. And then when the thing turns off, then they're allowed to relax, and then they absorb energy from the quantum vacuum, the virtual processes, as he calls it, of the vacuum. And what that translates into is a reduction in local gravitational energy. So it looks like weight loss, or it looks like dropping of inertia.
Well, that's again, like from my path, inertia and gravitational mass are different. Like when I've tried to teach or talk the difference. Like inertia from my physics lectures is your resistance to movement, and gravitational mass is your attractiveness, is like how strongly the field is curved around you.
Well, that's how we observe it. But like at the fundamental, subatomic quantum level,
Strong nuclear force.
Do they originate from the same process and the same interactions? That's
It's a strong nuclear force. How big is the nucleus, and how much strong nuclear force is it exerting? I mean, that
doesn't explain electron, because electrons don't have gluons in them, and yet they have mass. So I don't know, like, where to me it's a bunch of baloney, but I don't know.
So right now I'm going to go inside the Faraday cage and just double check the magnetic field at the sample with a separate Gauss meter and compare it to the Gauss meter on the side.
Okay.
I'll get the RF shut off.
Yeah. So having explained all that, I never really got to quite grasp where Alzafon was, like to see exactly what's happening there at the quantum level or whatever. It's a little bit vague because he doesn't talk about Compton frequency and stuff like that and how that
may not have been. Who was he? He was with Feynman. There's one lady in my my Buddhist sangha close by that actually grew up with Feynman. Like she literally they were living over in Berkeley. Compton Raleigh scattering, Compton scattering. Yeah, I don't have that memorized. I'm familiar with the term, but I haven't.
Compton frequency.
Compton. Compton. Yes, I've read it.
Yeah, that's the. It's a huge number. I mean, it's like for an electron, the Compton frequency. I can't remember the number, but it's like 10 to the power of 10 hertz or something.
Mm-hmm.
Also, get this. I just discovered something. You remember I was telling you, I was throwing out the number 3273. I saw some movement around there. I just checked the Gauss reading in the center of the waveguide where the sample is. Now the goal is to hit about 3,300. Turns out it's around 25 Gauss higher than this Gauss reading that we're getting off the side of the electromagnet. That puts it exactly at 3275.
Yeah, mathematically, that's what you would need, right?
We need 3,300 or 3,298 actually, right on the sample, and in order to get that, you would have 3273 on the side because there's a small difference between the center and the side of the field.
Yeah, that makes sense. You're gonna have a little bit of error in there.
Yeah, and that's when I saw the sample wiggling. So I'm going to turn this machine back on. We'll go back into that range.
Yeah, I like the idea of having the osmium in there. That's good because you have so much mass density there. Like it makes me think of what Townsend Brown reported about, having more mass in his gravitators. Like the heavier the dielectric, the more force there was, or the more gravitational thrust, as he called it.
Well, I want to cheat. That's what I've been. I want to. Like I said last week, I was going through and reviewing Lazar Lazarian theory, and going back into the element 115, and he talked about it. Paul Potter picked up on it, so it's in that handy dandy UFO book written by Paul Potter. But the element 115 was very oddly made. Ultimately, in the reactor, it was a wedge, right? That with a conical section at the tip. I don't know if this is that's a wedge with a conical section.
Yeah.
And then he was saying that it was a bunch of discs stacked like coins, right? Stacked on each other. And then if you think one of my aerospace mentors said that the saucers they're plus Russell Anderson, they're charged negatively underneath. But then as you get over the lip and start heading towards the center and in the middle, it's positively charged, right? Negatively. And then, you have an asymmetrical field topology where it's going back into positive. And then you get down into this, the waveguide going into the center of the reactor to the super dense heavy element that is, it's polarized. It's machined and then stacked in this funny polarization. So that positive charge keeps coming down into that moment. The foci of the flight reactor and that Mr. Lazar worked on. Mm-hmm. So I'm so then from that concept, gravito electricity, gravito magnetism. And so in the center of your craft, you have a super heavy element that's shaped as like an inward or downward vector. Mm-hmm. And then, at the larger scale, you have a negative field that's repulsive, right? So
you mean like a negative energy, as they might call it?
No, I don't think there's negative. If there's negative energy, that's going to be like something that's going on the hull, a metamaterial effect. So there may be negative energy density, but again,
well, that's supposed to be like an expanding, where space expanding. That's what they call it.
Okay.
Negative mass energy will cause space to expand, and positive mass energy causes it to contract.
Right.
So I don't know. That's just what I've heard.
Yeah. In my astronomy classes, we talked about negative and positive curvature of space-time. Mm-hmm. And here, it's academic, and we're at that point in my path, it was mathematics, right? We're always dealing with the first quadrant, which is positive, but then after a while, you figure out that there's this, if we're dealing with positive, and we've got these four quadrants, then you can get down into third quadrant where it's negative, or, and Feynman even talks about that, and that there was a bad concept for a while in Berkeley where they were saying that antimatter moves backwards through space-time, or it moves backwards through, well, you can't. It moves against the flow of time is what the idea that they were trying to communicate. And that was a mathematical concept because these theoreticians were just using pure mathematics. So they go, oh, well, we've got positive, we got negative. Space-time is always moving this way, but it's negative, so it can move backwards in time. So I don't know. That's just my over years of mathematics. No, I didn't do good enough. Okay, go back to the basics. Oh, okay. A little victory.
That stuff, it just gets so detached from reality to me. I don't know.
I agree.
It's over my head.
Well, yeah. But so with the concept of negative mass being able to negatively curve space-time. So in negative curved space-time, if you put an equilateral triangle on it, the interior angles add up to a greater than 180 degrees. I hope I still have that basic geometry, right? In Euclidean space-time, the interior angles of a triangle equal 180 degrees.
Mhm.
In negatively curved space-time, the interior angles are greater than 180 degrees. And then in positively curved space-time, the interior angles are less than 180 degrees.
Okay, that makes some sense. Yeah.
But,
I
yeah.
think I heard the Bob Lazar interview. I listened to that with Joe Rogan, and I remember him saying that this actor thing he was working on, he would feel like he was being pushed away from it, like there was a repulsive force on his hands, and they would try to
Right.
push something toward it, and it would just be pushed away, like there's a strong repulsive field coming off of it.
Right. So would that be like an outward expanding, rotating field?
Yeah, if you want to think of it, if you want to use that language, like it would be expanding space-time, or a negative curvature, or whatever.
Right. So that's a density. Yeah, my understanding of element 115 is that it is like the heaviest element that our universe supports. Hydrogen is the lightest element, but then that goes down to the quark structure, yeah.
Yeah.
So that's in the nuclear engineering books that I saw at UNM in 2013-14, they actually do teach about the island of stability at the senior level of undergraduate classes. It's in the textbooks nowadays. So that's, I don't know, for what it's worth.
Mm-hmm.
But yeah, so it was in that Joe Rogan. No, there was a Jeremy Corbell and Knapp interview, and they had a little bit of supposedly why Bob has continued to receive a bunch of shit is that he took one of the fuel samples, or the fuel pellets, and he ran away with it. And it's super rare. There's like, I want to say 500 pounds of it or so was given to the United States sometime, if what he's saying was true. But so one of these shaped fuel pieces he ran away with, and so that's why he's continued to get a bunch of shit from the government or the deep state, because they want that, that it would prove everything fucking true if he ever came out with it. But in the video, they video recorded it, and they show like a laser light bending around it, which, if I recall correctly, he had built some sort of low-level particle accelerator and could start to get the gravitational effect out of it. And then he would turn it off, and they were shooting laser light over it, and the light would just go whoop and turn. So yeah, curvature of space-time, rotational field.
And so what does that come from? You think about, okay, so element 115, I imagine, would have a very, very large nucleus.
Yep.
And so it's got some kind of a spin going on, so you have a very large, massive, dense nucleus that's spinning, or I don't know, as they say, quantum spin.
It's vibrating, and it's doing some frame dragging around it, right?
Yeah, frame dragging or gravitomagnetism or whatever, So yeah, it's means it suggests to me that it must exist in more materials than just element 115.
Yeah, that's what I was thinking about that. There's like technium, it's like element 43 or something.
Technetium?
Technetium, yeah, doesn't exist here anymore. It's everything that's on Earth is man-made.
Mm.
So maybe that's, I mean, maybe not. I don't know. We're brainstorming right now.
Bismuth,
Yep.
bismuth has, like, it's in the same column on the periodic table, so it's got a nuclear spin, but I haven't been able to do anything with bismuth so far that's really notable. There's got to be, I think it has to be, the reason for that is because of its diamagnetism. In order to mess with the nucleus, the nuclear orientation and all this, you've got to find a way to tap into the nucleus and polarize the nucleus, the nuclei. So,
well, if you have an active nuclear moment in the center of your vehicle, pulsing at the wavelength that the vehicle is, and then your whole material starts, amplifies that, is the scale. Yeah, there's been all these like arguments about what is a scalar effect. I'm like, well, the whole material is your scalar. That is a one-dimensional amplification. So creating the right metamaterials that scale the energy that's coming off of the flight reactor, and then the vehicle has to be shaped. It's got to be symmetrical, because you're, rotating field upon a rotating field upon a rotating field, and you're trying to find that buoyancy and then create the asymmetrical direction that you want to go, or the asymmetrical field topology in the direction that you want to go. And then that gets into the 4-wave mechanics that Jeremy had brought up, where they use like 3 different waveforms in order to generate a fourth, the overall waveform and then you apply that to 3-dimensional topology, and then you get an asymmetrical field, and then you just learn to rotate that in whichever direction you want to go in by charging your sectors correctly. The vehicle thinking quadrants, right? Like, I've talked a lot, but I got to get back to Jersey, and we've got to finish up some of these little things and try to play around with some fancy ceramics or the correct dielectric ceramic materials. But it's something that my subconscious has said for years is like, if you want to understand space flight, start trying to build a miniature star, right? Or use the same physics as a star. Mass concentration, and then rotational energy, and then an active nuclear moment. So you have a vibration. So that's just, that was a little, I used to say it a little bit better. If you want to travel between the stars, use the same physics as the stars. Plasma and fusion, I think, is maybe the first answer, the first level. So I don't know. I'm just enjoying talking with you, Wayne.
Yeah, that's interesting.
Thank you. I'm just sharing.
Well, like Tesla said, nuclear energy, at its fundamental sources, like the wheelwork of nature. Like everything has spin, so it's like everything is a wheel that's spinning. All these particles, and all they store all this energy in angular momentum, or whatever. I mean, I know physicists don't. They say, "Oh well, nothing's actually spinning. Like it's not literally spinning like a ball."
Mm-hmm. Mm-hmm.
And yet they say it has angular momentum, and they say, but spin is not literally spin.
It's polarization. It's gravitational polarization.
It's where
I mean, that's spin is polarization. Like how think about like a neutron star or a pulsar.
it's true. It's like
So yeah, you'll
magnetic. It's the magnetic field is intrinsic with so-called spin. So yeah, I mean, going any in my mind is speculation.
so Mark, you're just fiddling with knobs right now. What's the what?
I'm trying to put it on a strong pulse and then a basically 10% duty cycle. 10% duty cycle, I'm upping the frequency by 10 times to 830 hertz. I also bumped up the power a bit.
Let's see, we have a Shmuel Shuvak. That's what's in the Elzaphon book. Yeah, it's gotten quiet on YouTube.
I think we lost their attention with all their blabbing.
Yes and no. It's Mark doing it, and you've got 1,000. No, over 100,000 subscribers.
15 live watchers right now. Running these experiments is about as exciting as watching paint dry.
Yep. But we're also trying to, we're trying to put the vibe out there, and it's like a ripple. We're throwing a stone into a pool and hoping we get some good reflection back.
So this is the RF generator Mark sent me. It's his old 9 gigahertz one.
Oh, 1 second. Let me move spotlight so you can show that. Go for it, Wayne.
Yeah, I was just showing. This is your old RF generator you sent me, and so I've been doing the setup here too, and an amplifier. And so it's pretty simple. It just comes right out of here and goes into an amp. And then I made this Faraday box containing all the RF, I hope mostly. 5 layers of aluminum foil. So I was trying this the other day. This is a wave guide here with the RF comes into here, and then this is a big magnet. And so I was hanging a little piece of aluminum in there, seeing if there is a relationship between the weight, and it was hard to say. I mean, it did, the numbers did move around a little bit here and there, but it's hard to make a cause and effect relationship. My cat's losing his mind here. Well, I think I'm going to duck out here, Mark.
Yeah, I think I'm going to call it a night too. My eyes are starting to bleed.
Yeah, we can, if you could, I guess you got some okay video footage of that. And if you could,
We'll have
Post
to
it.
watch it a couple times to analyze the data.
yeah,
Watch a video. The only thing worse than watching paint dry is watching a video of paint drying.
Oh, make sure it's leaded paint and you don't eat it.
well, you just got to do lots of editing and get somebody, get a narrator to talk really fast and show lots of visual effects, and you'll retain some attention and massage the YouTube algorithm. And yeah,
We got to go back and figure out that frequency, the specific field density where you are at, and try to turn that into like a pulse width.
Yeah.
The geoid, the mass, the field mass concentration came out. No, that's not right. I'll have to, I'll figure it out. We'll talk about it over the week. Okay, well, ooh, I'm on YouTube. I'm talking, so. All right, I'm gonna punch out too, guys. So
Peace out, everyone. Thanks for tuning in. We had a really nice stream. There was like, I think there was a peak of about 20 people here. We got Jeremiah, Sean, Esoteric Gold is here, Shmuel Schubach, Curtis Hom, Phil Cosmos, Mr. Private was here too. Harold Tavares, he's always fun. Phil Cosmos again. Alien Girl 111. Yup. I made her a mod too. She can clean up all this craziness. So yeah, that was a great live stream, and peace out till next time.